Welcome to this explainer, where we're going to zoom far, far past the limits of human vision, right down into the absolute invisible building blocks of the universe. Today, we're revealing how the bizarre, totally counterintuitive rules of subatomic physics aren't just some abstract theories on a chalkboard, but the literal foundation that powers your everyday life. We're talking about a realm where the impossible happens constantly, and honestly, it is absolutely fascinating. Let's get into it.
I mean, it sounds completely impossible, right? If I asked you to stand in your kitchen and your living room at the exact same time, you'd think I was crazy. But to answer this question, we have to entirely abandon our classical understanding of reality. You know, the physics of throwing baseballs and driving cars, and enter the microscopic realm where the normal rules of the road simply do not apply.
Okay, let's dive right in by defining our core term here. The word quantum actually comes from Latin, meaning how much, and it refers to the smallest, indivisible packet of energy. This was a massive concept established by the brilliant physicist Max Planck back in 1900. He fundamentally changed how we view energy, basically proving that it doesn't flow in a continuous smooth stream like water from a hose, but rather in tiny, separate and distinct chunks.
So here's our roadmap for today. We're going to explore mind-bending quantum paradoxes, check in on Schrödinger's cat, and look at the historic clash between Einstein and Bohr. Then we'll review some foundational texts, uncover everyday quantum applications, and finally, look at the single biggest unresolved problem in all of physics.
All right, part 1, the weirdness of the quantum realm, which is basically where classical physics just completely breaks down.
This is the line in the sand. Once we cross it, the physics of everything we can see with our naked eye completely falls apart, and a new, probabilistic reality takes over. And when we look closely at this world, things get strange fast. First, thanks to wave-particle duality, electrons aren't just solid dots orbiting a nucleus. They act as spreading waves of probability. Second, they make what we call quantum leaps, absorbing and emitting energy only in strict quantized packets. And third, through quantum entanglement, particles can actually become mysteriously linked, instantly mirroring each other across vast, vast distances.
Moving on to Section 2, Uncertainty and Schrödinger's cat, or the absolute absurdity of unobserved states. So these tiny, microscopic probabilities, they create massive, literally headache-inducing philosophical questions for us up here in the macroscopic world. Back in 1935, to highlight this exact absurdity, Erwin Schrödinger proposed a hypothetical setup. Imagine a living cat is locked inside a thick, closed steel box. Inside this box with our cat is a lethal mechanism, a vial of deadly hydrocyanic acid that will be shattered by a hammer if a Geiger counter detects the decay of a single radioactive atom. The catch here is that the decay of that atom is a purely quantum event. It is perfectly random, with exactly a 50-50 chance of happening over the course of an hour.
Right, so the door is closed. An hour passes. Is the cat alive or dead? Without a human observer to open that box and actually make a physical measurement, classical physics is completely stumped by this simple question. Our brains want to say it must definitely be one or the other, but the math tells a very different story.
According to the strict rules of quantum mechanics, until an observer opens the box and forces reality to make a choice, what we call collapsing the wave function, the system remains in quantum superposition. The math straight up states that the atom is both decayed and undecayed, which means the cat literally exists in a blurred mathematical superposition of being both alive and dead at the exact same time. No way around it.
And this inherent blurriness builds directly on Werner Heisenberg's famous 1927 uncertainty principle. Think about it. In classical precision, we expect to measure a car's speed and location at the same time with 100% accuracy. But Heisenberg proved that at the quantum level, the very act of measuring alters the particle. If you bounce a photon of light off an electron just to see where it is, that impact permanently changes the electron's speed. We can literally never know both its exact position and momentum simultaneously. It turns out the universe has a hard-coded limit on what we can actually know.
Which brings us to Section 3, Clash of Geniuses, featuring the ultimate heavyweight bout of Albert Einstein versus Niels Bohr.
As you can probably imagine, not every scientist was thrilled about discovering a universe built on random probabilities, blurry measurements, and spooky connections. Albert Einstein vehemently rejected this probabilistic universe. He firmly believed there had to be an underlying deterministic reality, hence his incredibly famous quote, "God does not play dice." Einstein argued that entangled particles were basically just like a pair of gloves separated into different boxes. If you open one box and find a left glove, you instantly know the other one is a right glove. No spooky connection, just predetermined properties from the start.
But Niels Bohr pushed right back.
Bohr argued that the particles genuinely do not have defined properties until they are measured, and that the quantum link is very, very real. And as wild as it sounds, experiments, starting with physicist John Clauser in 1967 and others later on, actually proved Bohr right. Testing thousands of entangled particles proved that these quantum links genuinely exist, instantly affecting each other, completely regardless of the physical distance separating them. So, Einstein's glove analogy? Yeah, it was actually wrong.
All right, let's look at Section 4, the best sources to learn quantum and how we navigate all that complex math.
To truly grasp these concepts beyond just the fun thought experiments, you really have to look at the foundational texts. It's so fascinating to see how our mathematical understanding actually evolved over the decades. The story starts with Paul Dirac's 1958 book, which laid down the foundational notations. From there, it shifts to Richard Feynman's legendary 1960s lectures. He brilliantly championed physical intuition over complex math. The evolution continues through Lev Landau's challenging 1970s texts on deep phenomena like superconductivity, carrying us right up to modern graduate-level texts like Saccharie's, which tackle advanced symmetries.
Moving on to Section 5, Everyday Applications, how all this weird math actually powers modern life.
Now, at this point, you might be sitting there thinking this is all just abstract, microscopic philosophy. But far from being merely theoretical, our understanding of the wave nature of electrons is the bedrock foundation of the physical technology you rely on every single day. By manipulating quantum energy bands, we created silicon semiconductors, which allows literally billions of microscopic transistors to fit right inside your smartphone. Quantum mechanics gave us the lasers at your grocery store checkout, the life-saving MRI and PET scans in hospitals, and even ultra-secure quantum cryptography, which uses the entanglement of single photons to create completely unhackable digital keys.
And it gets even better. Quantum mechanics literally explains why we are alive, because it's the exact mechanism that explains how the sun shines. Classically, hydrogen atoms in the sun simply don't have enough kinetic energy to overcome their mutual repulsion and fuse. But because they behave as probabilistic waves, they occasionally tunnel straight through that energy barrier. This quantum tunneling allows fusion to happen in the first place, releasing the sunlight that sustains all life on Earth. How cool is that?
Finally, Section 6, Quantum Mechanics versus Relativity, the ultimate divide in modern physics. So, as we wrap up this explainer, we have to address the elephant in the room. Despite all these massive technological successes, we are facing the biggest unresolved problem in modern science. We currently have two wildly successful frameworks for understanding reality. On one hand, quantum mechanics flawlessly describes the incredibly tiny world of subatomic particles using probabilities. On the other hand, Albert Einstein's general relativity flawlessly describes the macro world, the smooth, deterministic geometry of massive stars, galaxies, and gravity. The problem? When you try to combine their mathematical rules, they completely contradict each other. They flat out refuse to work together.
Which leaves us with this final, massive question. Will humanity ever actually find a single, unified theory of quantum gravity? Will we ever discover the missing mathematical link that finally connects the blurry, random paradoxes of the quantum realm to the massive, deterministic gravity of the cosmos? That is the ultimate frontier. And hey, perhaps it's a question that one of you watching this explainer might one day answer. Thank you so much for joining me on this deep dive, and keep your curiosity alive.